Hello, my dear students. Today I am going to discuss about the relative velocity in translating and rotating frame of reference. So we know this is a very tricky and difficult topic. So we'll be doing it step by step. First of all, the first case is case 1. If the frame of reference is translating, in this case, how we are going to write about the velocity of one point with respect to other. So this, as usual, we have been studying it, right? If two frames are there, you can see here. One is the ground frame and another one is this frame, which is translating frame. It's not rotating, by the way. And there is another particle. Let's say this particle is P. And from this frame, what will be its velocity? Like this. So as usual, traditionally, we note this, that R21 vector means the position vector of P with respect to the observer 1 who is at the origin here, right? So this is R21 vector equal to R2 vector minus R1 vector. And if we differentiate it, then we'll be getting dr21 by dt is equal to dr2 vector by dt minus dr1 vector by dt. And dr21 by dt is nothing but velocity of point P with respect to 1, means v2, velocity of 2 with respect to 1, v21 vector equal to dr2 by dt is what? Is nothing but your velocity of 2 with respect to the ground observer, dr2 by dt with respect to this ground observer only is the velocity, right? Because the rate of change of this position vector with respect to ground minus dr1 by dt is what? Is the velocity of this frame 1 with respect to the ground observer. So as usual, we know this. This is pretty simple, right? So this is case 1 when the frames are translating. For example, this frame is translating. It's not rotating, by the way. Then as usual, we can write. Now I'm going to take up the next case, which is the difficult one. Let's see this case number 2 when observer is rotating without translation. Okay, so here let's say this is a fixed inertial frame, right? This one is, here I have shown I cap, j cap like this, and this one is fixed, and here this is a rotating frame. The red one is a rotating frame, and it means the observer here is rotating. It means that his coordinate axis keeps on rotating, right? So what will be the velocity of this point? How we can interpret all these things, we have to see. Let me take you up this example over here. So here, let's say that this is a disk which is rotating, and on the center of the disk, one person is standing over here. And then let's say there is another coin like this. Coin is kept here. And if the disk is rotating with omega, so person will also rotate with omega. So his coordinate axis is also going to rotate with the same omega, right? And he will observe the coin's position, right? This is the coin. So coin may be slipping like this on this disk. Coin may be slipping. So let us see here. So here v rotating, I have written vrot means v rotating means in this rotating frame of reference, what is this velocity this rotating person is seeing? So we can see here in this example, if the coin is slipping on the disk, so let's say it is slipping with v rotating. So in this case, I can say that this person will see that, he will see that on this disk, coin is slipping with some velocity, right? So that is your v rotating. I gave you this example. Okay. So I can say that, let's say that here two observers, one observer is on the inertial frame and another observer is on the rotating frame. Both are coincident. So I can say that at any time t, you see at any time t, both the position vectors coincide, right? So that's why I have written r of p in the rotating frame is equal to r of p in the inertial frame. Let's say this is equal to r vector, right? And here I can say that if I resolve into components, so in this frame, I dash j dash frame, this is your I dash, and this one is going to be your j dash frame. This is x dash I cap dash plus y dash j dash cap, right? Similarly, in inertial frame, we have xi plus yj. So these two are, equal. It means their component may be varying, right? Because it is written in different frame of reference. But can we say that if we take the derivative of this, if we take this derivative, d by dt of rp, rotating frame is equal to d by dt of rp in inertial frame, can we say? No, absolutely not. We can't say like this. Both can't be equal. Their position vectors are coinciding, right? Like this. But taking the derivative won't be equal. Okay. So this is what we are going to prove. drp in rotating frame, ROT I'm writing, is not equal to drp in inertial frame. And here I can also say that di by dt, this is a constant unit vector. If you take the derivative, it will be 0. But di cap dash by dt is not 0. You see, di cap dash is after some time this will be here, right? And j cap dash will be here. So its derivative won't be 0. So this vector keeps on changing. Its direction keeps on changing. Okay. Now I'm going to prove the relation between dr in inertial and dr rotating, right? So what is this relation between this? Let's find it out. So let's say this is inertial frame. It's a very important relation. And in fact, this is going to make the foundation for proving the Coriolis and the centrifugal force, which is very, very important. Okay. So let's see step by step here. So in inertial frame, if this particle is just, translating, then we can say that this is dr vector in inertial frame, which is nothing but your elementary displacement. Okay, at time t plus dt I have written. So let's say at time t plus dt, this has the displacement dr inertial, right? So you got it. So anyone who is observing from the ground frame about this particle, he will see this elementary displacement in time dt. So now I am in a rotating frame. Let us see this very, very crucial, very minute things, many minute concepts are there here. Very important one. Let us see here. Now in rotating frame, in, time dt interval at a particular time here, what will be this one? Let's say this particle here is at time t. This one is time t position. Now, if just a simple rotation case is there. So if this one is rotating and let's say that particle is stationary, let's assume that there is no velocity in inertial frame. So this particle will be stationary, right? You see, this particle is going to be stationary. Let us say in inertial frame, there is no velocity. Okay, just this frame is rotating in anti-clockwise sense. So he will see that this observer is going to see that the elementary displacement of this particle in dt time interval will be what? In opposite direction, right? Because if this guy is going in this direction, so he will see that this particle is going to be in opposite direction. You can feel, for example, you are on the center of the disk. There is another particle here and the disk is rotating in this direction, right? So in which direction this point P is appearing to be rotating? In opposite direction, in this direction, right? So what will be its displacement? Which is minus d theta cross r. Why I'm writing this d theta cross r? Because we know omega cross r is this velocity in this direction. Omega cross r. So if you just multiply by dt, you'll be getting d theta cross r. So the direction is going to be in opposite one, right? And that's why I put here minus sign. So if this one is dr inertial is 0, it means this is not there. So he will see that there is one displacement he will be seeing just due to his own rotation. Now, let us say that in time interval dt, this inertial observer is seeing the elementary displacement dr inertial. So this observer will also see this one component, right? So both these displacements he will be seeing. So that's why I have written over here, think of the superposition displacements dr inertial and minus d theta cross r to get dr rotating, right? It means whatever he is seeing, the displacement, elementary displacement, is the vector sum of this green one and the red one. So that's what I have written over here. Okay. So you can think of, okay, just using the superposition. You have stopped this one, means if there is no dr in, there is no velocity in inertial frame. So you stop this. So you get this one minus d theta cross r. Now you again think, okay, this is also elementary displacement is also there. So vector sum of these two displacements, this guy will be seeing, right? So that's what I have written over here. dr rotating is equal to minus d theta cross r plus dr inertial. That is very, very important to understand. Once you have got the feeling of this, rest everything is mathematics. Nothing much will be there. Let's see here. So I can say that dr inertial is equal to dr rotating plus d theta cross r. From here we got, right? Minus I have taken to the left side. Very, very important one. Okay. So now we have proved this. We have proved the elementary displacement in inertial frame is equal to elementary displacement observed by the rotating observer plus some d theta vector cross r vector. I have divided by dt. So you'll be getting dr by dt in inertial frame is equal to dr by dt in rotating frame plus d theta by dt cross r, and this is nothing but your omega. So very nice result we got. Dr by dt in inertial frame is equal to dr by dt in rotating frame plus omega cross r. Now you can think of that this velocity in the inertial frame is the vector sum of velocity of the particle seen by the rotating observer plus omega cross r. Very, very important. And it is going to forming the basis to prove Coriolis and the centrifugal force. This is exact equation we will be taking up. So in the next video, I'll be proving this centrifugal and the Coriolis thing also. Okay, one important point to be noted. Although we have proved equation 1, this equation 1, this one, although we have proved it for this position vector, it is going to be applicable. This equation is going to be applicable for all vectors, not only for position vector. Very, very nice equation we have. Means rate of change of this position vector in inertial frame is equal to rate of change of the position vector in rotating frame plus omega cross r. So we can also say that rate of change of any vector b vector in inertial frame is equal to rate of change of that vector in rotating frame plus omega, which is the angular velocity of the rotating frame cross the vector itself. So this is a very important one. Okay, now let's take a couple of examples over here to explain it, to illustrate this one. So this example is saying that here is a disk which is rotating in anti-clockwise sense with angular velocity omega, radius r. Now there is one observer over here, right? Let's say this, there is no friction between observer A and disk. Yes, there is no friction. It means observer will be stationary, right? Because the disk will be, slipping over the observer. So we can say that here A is not going to move. This A is inertial frame, right? Fixed frame. So can I apply VBA is equal to VB minus VA? Yes, of course we can apply, because this frame is translatory. This is translating frame. So we know the velocity of B is omega r j cap, and as this disk is rotating, so about this omega r in upward direction and velocity of A is omega r downward direction. So VB minus VA, you see omega r j cap minus omega r. This one is j cap. So which you will be getting 2 omega r j cap. So A will see that velocity of B is in upward direction having the magnitude 2 omega. Or we can also say that, okay, now since this observer is stationary, right? So this line will be appearing to rotate with the same angular velocity omega, right? If this line is rotating with same angular velocity omega, so I can also say that you can write this velocity, which is the perpendicular to this line, is equal to omega into r perpendicular, and r perpendicular is what? 2r. So omega into 2r is going to be the velocity of this point in this direction. Okay, so we got this very important concept here. So we are going to get this 2 omega r j cap, and here also we are getting the same as 2 omega r j cap. So both ways we can think of. Okay, next example. These are all simple examples I'm taking just to illustrate the concept, and nothing complicated. Because once your concept is clear, then everything will be all right to solve any complex problems. So now in the second example, I'm taking that, let's say that person A is rotating with the disk. It means there is sufficient friction so that person A is rotating with the disk. Again, I'm asking you to find what is the velocity of this B with respect to A in this case. So now just intuitively tell me what velocity A will see all the time. 0, right? Because let's say you are standing here and your friend is standing here. Both are on the edge of the disk, diametrically opposite. So you will see continuously that B will be diametrically opposite to you all the time. So here I can say V rotating will be 0. All the time it is going to be 0, right? Because this is going to be your which frame? Is it a rotating frame or translatory frame? Now tell me. Because as there is a coordinate axis attached to this person. So this coordinate axis, as this one is at time t plus dt here, this is at time t. So he will see that this, this coordinate axis is going to rotate. So initially the coordinate axis is like this, and then after some time this coordinate axis will rotate. So this is a rotating frame, right? And in rotating frame, here you see there is no rate of change of this position vector. All the time, this AB vector will be seen in this frame, From ground frame, AB vector keeps on changing, right? This is with respect to ground. If you see, this vector keeps on rotating. But from this AB vector, this guy will always see that AB vector will always be. Let's say if this is your x-axis, so you'll always see that this B will be on the x-axis. Yes. So frame A is rotating with same omega. Yes, same omega. It's rotating, and B will always be diametrically opposite to A. So that's why we can say rotating here, velocity is 0, v rotating is 0, so vva is 0, right? Okay, now one more important point to be noted here is, in combined translation and rotation motion of any rigid body, we know how to write velocity of any point with respect to any other point lying on the rigid body. So velocity of 1 is equal to velocity of 2 plus velocity of 2 with respect to 1 we write, right? Which is nothing but omega cross position vector of 1 with respect to 2. This will be position vector of 1 with respect to 2. Okay? So I can say that velocity of 1 is equal to v2 vector plus omega cross r12 vector. Yes. Now tell me, in writing this, do we assume that point 2 here, this is a rotating frame? Do we assume? No, we don't assume it. We don't assume this observer to be rotating. If this observer we assume to be rotating, we can't write the velocity of 1 observed by 2 as omega cross r12. This is only true if this is not rotating. Okay? Particle 2 here is not rotating, it's just translating. So for translation only, this result is true, as we have been studying in simple kinematics. Okay, v1 vector equal to v2 vector plus v21 vector. And by the way, this is also going to be v12, velocity of 1 with respect to 2, right? So what I mean to say that here point 2 is not, a rotating frame. It's not a rotating frame. If it would have been rotating, he will all the time see 1 to be at rest. So we are assuming that 2 is, translating. It means this orientation of this coordinate system attached to 2 is not changing. If this is not changing, it means line joining 1 and 2 will keep on rotating with same omega, right? As the angular velocity of the rigid body. And that's what here. So this guy at 2 will see that particle 1's velocity will be omega cross r12 due to the rotation, right? He will see that this line is rotating. The line joining 1 and 2. It means position vector of 1 with respect to 2 will rotate. With how much? Omega cross r12. And once you come down to the ground frame, you will be adding up this velocity of 2. That's it. So this is important point. Sometimes you will have confusion. Oh, is this a rotating frame because it is lying on the rigid body? While writing this, we don't assume it to be rotating. Okay. Next case I'm going to do, it's important, the translating plus rotating frame. Now I'm going to club these two frames. What happens if the frame is translating as well as rotating? Second case, only rotating frame is there. First case, only translating frame is there, right? Now I have taken this frame 1. This frame 1 is rotating with angular velocity omega as well as its velocity, translational velocity is v1 vector. How we can write this relative velocity? Let's see. Now, velocity of particle 2 in rotating frame. Let's assume one frame which is only rotating but not translating over there, right? So basically we have the three frames here. One frame is the fixed frame here. Another frame is just rotating frame. All these are coincident. And the third frame is rotating plus translating frame. So as per the second frame, only the rotating frame, we know how to write this equation, right? From the rotating frame of reference. So velocity of 2 from the ground frame can be written as velocity observed from the rotating frame only plus omega cross position vector of 2 with respect to 1, right? This is velocity of 2. Where velocity rotating is just velocity appeared in a frame which is just rotating and not translating, what I said, right? Now, how I can write this v rotating in terms of this v1, v2, 1 like this? Now let's see. Now my frame 1 is what? Frame 1 is rotating plus translating, right? So here, what is v rotating? Can I say that if this guy 1 sees that this guy 1 is rotating frame plus translating frame, right? If this guy 1 sees that velocity of 2 is v21 vector, right? So velocity of 2 with respect to 1, it means who is saying? The guy 1 who is rotating plus translating. This guy is saying that v21 vector. Okay. Think very important one. So I am trying to find what is v rotating here. Now, if he comes down to the second frame, which is just rotating frame, right? So how do we find? For example, if you come down to the ground frame, what do? You add the velocity of that frame, right? Similarly, we are in frame 1. Frame 1 is rotating plus translating, and we are coming down to frame 2. Frame 2 is what? Let's say just second frame, which is just rotating. So when you come down to this frame, so v21 vector plus the velocity, translational velocity of this frame, right? Frame 1 you will be adding up, right? And that's what you will be getting the rotating frame's velocity, means velocity in the rotating frame. This is important, right? Just I gave you how to think of this. So v21 vector is velocity of 2 in frame 1, which is both rotating with omega and translating with v1 vector, as I said. When you come down to which frame? Just purely rotating frame, you add up the translational velocity of the frame, just like we do in the normal cases for kinematics relative motion, right? So now once we do this, you put this value of v rotating over here, and then finally you'll be getting v2 vector is equal to v21 vector plus v1 vector plus omega cross r21 vector. Okay, so we'll be saying what is your v2 vector minus v1 vector. I have taken to the left side. This is v2 vector minus v1 is equal to v21 vector plus some term omega cross r of 2 with respect to 1, r of 2 with respect to 1. So you see, in rotating plus translating frame, this is rotating plus translating frame, you see that this is not equal, means one more component will be there. v2 vector minus v1 vector is not equal to v21 vector. This is just only for translating frame. So we have got one more term over here. v2 vector minus v1 vector is equal to v21 vector plus omega cross r21 vector. Very, very important. Okay, and you will remember this equation. If the frame is rotating plus translating, how will you write the relative velocity like this? This is the relative velocity. v21 vector is the relative velocity. You will be writing how you will be writing. So v2 vector minus v1 is equal to the relative velocity in the rotating plus translating frame plus omega cross r position vector of particle 2 with respect to the observer in rotating plus translating frame. This is what we have proved. Okay, so do remember this important concept. Now I think your relative velocity concept is clear in all the frames, how we are going to write. Whenever it is purely rotating frame, remember this is the vector sum of, means velocity in inertial frame from the ground frame is the vector sum of the velocity observed from the rotating frame plus omega cross r. So this is the case of this relative velocity. Now let me take one example over here to apply this concept and see how it is happening, through how this equation is, taking up. Let's see, this is a rod. Let's say this is a rod. A rod is rotating about the end point, and there is a point here, A. Okay, it's a fixed point, and let's say the observer is rigidly attached to this point A, which is the midpoint of the rod. Okay, and now this observer is watching observer B. So naturally you can surely say that, okay, since this is rigidly attached and B is also on the rod, point B is also on the rod, so he will see that, observer A will see that the velocity of B will be 0, right? So observer A is rigidly attached on rod in this example, and what you have to find? Find velocity of B with respect to A using the above relation, this relation which I just proved. Okay, so you will naturally say that, intuitively you can say that, okay, velocity of B with respect to A is 0. But I am trying to apply this relation. Let's see how we can apply this. Now observe here that, is this frame A, it means which is rigidly on the rod, rotating frame or translating or rotating plus translating? So it is going to be rotating plus translating, right? Because if you observe this A, so A's velocity, if you see, so A is translating, right? A is translating with how much velocity? Omega L by 2, omega into perpendicular distance L by 2. Now he's translating in this direction. This is his translating velocity. Now he's also rotating. Why is he rotating? Because he is rigidly fixed to the rod. As the rod rotates, his coordinate axis will also rotate, right? After some time, after dt time here, his coordinate axis will be like this. So there will be some angle. So his coordinate axis is going to rotate by the same omega. That's what I have shown over here. So this is rotating with angular velocity omega, as well as he is translating with the velocity of omega L by 2. Now let's apply this one. So we have to prove that as per him, velocity of this B is going to be 0, right? Using this relation. So apply this concept here. It means this is B and this one is A. So velocity of B minus velocity of A is equal to VBA vector, velocity of B with respect to A, plus omega cross RBA. Once we have identified that this is rotating plus translating frame, this is very important. Once we have identified R plus T frame, then we can apply this formula over here. So do remember, you have to identify which frame is this. Once you have this, apply this. Now, velocity of B minus velocity of A is what? We know from the ground frame. What is the velocity of B? What is the velocity of A? Velocity of B is omega L by 2 from ground frame. Means this observer who is fixed. He will see that B's velocity is how much? Omega L. And A's velocity is how much? Omega L by 2. So, minus omega L by 2, BB minus BA. And direction will be J cap, right? I have shown. This is equal to BBA vector, which we have to find, plus omega cross RBA. Now, this is also rotating with how much? Angular velocity omega. So this omega is omega of the frame of reference, right? In our formula over here, this omega is omega of the frame. So now, he will see that whatever the omega of this, about this observer, about this observer also same omega will be there, right? Because omega is the property of the rigid body. So we can say that this is going to be omega cross R of B with respect to A. This is your RBA. So RBA vector is this one. So omega cross RBA will be how much? Omega L by 2. We know omega vector is outward, out of the plane, and RBA is in this direction, so out of the plane. So it's going to be, curl your finger, omega cross RBA. So simple velocity funda is also there. Now omega, how we write? Omega cross R. So we know omega cross R is going to be just in upward direction, means in along J cap. It means omega L by 2. And once you do, this is going to be omega L by 2 J cap, omega L by 2 J cap. This is going to be 0. It means what? Cut. Velocity of B with respect to A is going to be 0. And intuitively also, what we had proved, velocity of B, A must be 0, right? As A and B will always be facing each other. So hence we applied this. So I hope students, all these minute concepts are clear. And once you understand these concepts, this is going to form the backbone to prove out the Coriolis and the centrifugal force. So very important one.